Good evening, everybody. This is week 3, and if you've worked through the book, through chapter 3, you know that this is one of the more complicated weeks. Don't get discouraged just yet. We have a lot of time for all this stuff to settle in and solidify in your brains, and I will promise you, you will be able to get some of these questions correct. Before we dive into today's chapter, anything about what we've done so far? Any questions?
Nah.
No? Okay, good.
No, I'm pretty good.
So I assume you can see my screen?
Yep.
Yes.
So again, just a reminder to sign up for testing if you're local to Rochester. We still have plenty of room, so don't get worried about this just yet. But just keep this on your mind and sign up for your FRN. And this is important regardless of where you are. You need the FRN to take the test, regardless of whether it's remote or in person. You need your FRN. So get that squared away. And then once you have that, you can think about signing up for the actual testing session. So today we are talking about electricity, different aspects of it. And electricity is kind of important. Oh, a little bit of ham humor. Electricity is important because, of course, our radios run on electricity. Our waves that we send out are electromagnetic waves, so they have the electro in part of their name. So that plays a role. And we also want to make sure that we have a basic understanding of how electricity works when it comes to radio. This will help you, for example, when you set up your station and you need to buy a power supply and you need to figure out how big that power supply needs to be, or when you install a radio in your car and you need to figure out how thick a piece of wire you need to hook up that radio to your battery, and so on. So when you look at a battery, it doesn't matter whether it's a AA battery or your 12-volt car battery or a 9-volt battery. One thing that is pretty obvious is that there are two different poles on it. And one is called plus and the other one is called minus. And there is actually a reason for that, because when we talk about electricity, we have electrical charges that can either be positive or negative. And opposite charges, one positive one negative one, they attract each other. A positive one and a positive one, they will repel each other. So this attraction of charges is an important concept. When we have these charges and we push them through a wire, meaning we have a flow of electrons, these are small charged particles. When we have this flow, we call this an electrical current. And if you have a lamp connected to your battery, there is a current that flows through that lamp, pushed out by the battery. And here's a little bit of physics. We don't really need to know about that, but what is important is that the electrons move in response to what we call the electromotive force. And this will show up in some of the questions this term, so keep that in mind. The electromotive force is what causes electrical current to flow. So what is a current? A current is that movement of electrons, and we measure it in amperes. And we use a capital A as the unit for ampere, or we just call it an amp. And we measure it by an ammeter. And when we see a current in an electrical formula, then it is represented by a capital I. So we use the capital A as the unit symbol, where we say this battery is pushing out a current of 5 amps, so it's 5 and a capital A. But when we try to calculate a current, or we calculate something based on a current in the formula, the current would be represented by the capital I. This is a little bit confusing, but we'll keep on seeing the same concept. The voltage is the amount of electromotive force that we have. Sometimes it's also called the electrical potential, and we measure that in volts. And we use the capital V as the unit symbol. We use a voltmeter to measure the voltage. In formulas, we use either the capital E or the capital V. In this class, it will be the capital E. So depending on which school of thought you were brought up in, where you went to school, you either use the capital V or the capital E. We are using the capital E. There's one more thing that we need to know about, and that is resistance. Resistance is the opposition to the movement of electrons. So the resistance is the opposition to an electrical current. We measure it in ohms by an ohm meter. And in a formula, we use the capital letter R. The unit symbol is a Greek letter omega, and you see that here. So we've already learned about one Greek letter last week for the mu, which we use as the unit prefix for micro. And now we have another one, the omega, which we use for ohms. This resistance is a little bit like friction, and it turns electrical energy in heat. If you've ever touched one of these old incandescent light bulbs, after it has been on for an hour, you know how hot that thing gets. And that is because there's a resistance in there, and it turns electrical energy into heat. When we have a material that allows current to flow, we call this a conductor. And a conductor has low resistance, so low opposition to the movement of electrons. An insulator will block the flow of current, and it has a high resistance. Does that make sense? One allows the flow of current, a conductor, a piece of wire, for example. The other one blocks the flow of current, a piece of glass, for example. Glass is a very good insulator. Sometimes it makes sense to find an example that is not an electrical example to demonstrate electrical concepts. And the flow of water oftentimes is a good way to show how that flow of electrons might actually work. So when we look at this, whoops, where did we go? When we look at our electrical circuit here, we have a battery, and when we measure across the battery, we can measure a voltage, and we have some wire here, and when we look into that wire, we can measure that current, that flow of electrons. So over here, we have the same concept based on a pump that pumps water. And the pump creates water pressure, and that is analogous to our voltage. So it's the same concept. It's the power to push something through something else. In the case of water, we push the water through the pipe. In the case of our electrical circuit, we push electrons or the current through our wire. And if you want to measure the flow rate of our water, we need to actually put something inside that pipe to measure that flow. And the same is true for the current. So the flow is the same as our current, and the pressure is the same as our voltage in an electrical circuit. Does that make sense? Okay. So the voltage so the voltage from a voltage source causes that current to flow. That is one of the fundamental concepts. Resistance is a material's opposition to that flow of current. Voltage, current, and resistance affect each other. The higher the push is, the higher the voltage is, the more current will flow through a given resistance. And this is the best way to show this. So we call this Ohm's law, and we will see the mathematical expression of Ohm's law in a few slides. But just look at this. You have a wire, and the voltage is trying to push that current through that wire. And the resistance, the guy with the hat, is restricting how much current can flow. So if you understand that, you understand Ohm's law. And then it's just a little bit of math. But this is what happens with current, voltage, and resistance. So if we change our resistance and we have the same push, the same voltage, we have a higher current that flows. If we lower how much we push, we lower the voltage, we have a lower current that will flow. Does that make sense? Kind of. Okay. We don't want to
Carl,
get.
this is like Chinese, but I think I'm with you. We'll see later on.
Okay. Okay. You know how water behaves in a pipe or a hose. You have a big hose, you can get a lot of water through that. You get 100 gallons per second. You have a tiny little hose, you get a trickle, maybe a cup per second. So the size of your hose is your resistance.
Okay.
If you push really hard with a tiny hose, that water will come out the end and it will go 100 feet through the air.
Yes.
That's the flow. That's your current. That's the electrical current. So you push really hard. You have you constrict how much water can flow. It will still come out, but not quite as much as if you have the big pipe.
Okay.
So again, I don't want you to get a PhD in physics. We keep this very basic. But these three things somehow interact with each other. And we'll get to how they interact with each other in a few slides. Before we do that, we have to look at two different kinds of currents.
Yep.
We have current that only flows in one direction, and we call that direct current. And if you have a battery that has a plus and a minus on it, DC, direct current, is what comes out of that. When we look up here, we have the magnitude and the direction of the current on the axis that goes up and time on the axis that goes over. So here we we switch that current on, and then we switch it off again, we switch it on again, we switch it off again. It always goes in the same direction. This is still direct current. Current that flows in one direction for a certain amount of time and then reverses and goes in the other direction, we call alternating current, or AC. And what comes out of the outlet on your wall is AC. So that actually switches directions 60 times per second. And we see this here. So it goes up, goes down to 0, and then goes the other way. So the electrons move back and forth and back and forth. So this is what we would create if we wanted to transmit a signal. We would create alternating current AC and then push that out the antenna. Our radio runs on DC, at least most radios. So we would need like a car battery or solar panels or a power supply that converts AC into DC. And then we would use that to power our radio.
Hey, Carl, I got a question on that.
Yeah.
So if your house is alternating current AC and you see like on your plugs that say 60 hertz for your power, does that mean that everything plugged into your house is like turning off and on 60 times a second?
Kind of. If your eyes would be a lot faster and you had LED lights, you can actually see that they turn on 60 times per second. With incandescent light bulbs or fluorescent bulbs, you would not see that because whatever is in there glows for a little bit. So it would not go off completely. But with LED lights, you would actually see that they come on, come off, on, off, on, off, on, off. But our eyes are too slow to react to that.
Oh, okay.
If you have a TV set or something like that connected to that AC current, it will actually convert the AC to DC. So it would not turn off and on 60 times a second. And there are, again, devices in there that will bridge those gaps in between these two peaks here. So we have a peak here, we have a peak here. So there's a capacitor actually in there that will bridge that and provide power, store power, and provide power while that current swings the other way.
Oh, okay.
Carl, Frank,
Yes.
you're the car mechanic, right? Are you the mechanic, Frank?
No, I work for a seed and fertilizer company here.
Oh, all right. I was gonna say years ago, us younger guys, we wanted to put all these fancy light on our cars. The
Yeah,
headlights, those LED headlights. And
yeah.
on some cars, they ended up selling an additional, like an ohm resistor pack that you plugged in from the car. Then it was the intermediary between that LED headlight, and that's what stopped it from flashing.
Oh, okay. I'm just thinking like, well, if it goes up and down a bunch of times, does that mean it's turning on and off? So that was a good way to explain it. Thank you.
For some devices, that's true. For other devices, there's something in there that stores energy for a little bit.
Oh, okay.
So we've already talked about frequencies and hertz. So the frequency of our power that comes out of the wall outlet is 60 hertz. In order to have current flow, we need a path from one side of our battery to the other side. And when we create that path, we call that a circuit. And again, thinking of water, if you just have a pump, the water is not going anywhere. You need a pipe this conductive path that we have in a circuit to actually bring that water to that faucet in your bathroom. When we look at basic topologies, layouts of our circuits, we have two basic, very basic layouts, a series circuit and a parallel circuit, and we look at both of them. This is what a series circuit looks like. If you've ever worked with Christmas lights and one bulb burned out and the whole strand just stopped to work, that is a series circuit. So we have some power source, a battery in this case, and then light bulbs, and the plus wire goes in one side of the bulb, comes out the other side, goes in one side of this bulb, comes out the other side, and does the same thing on the third one, and then goes back to the battery. And if I cut this circuit anywhere, everything stops to work, just like your Christmas lights. If one bulb burns out, all the other bulbs will go out. Now, newfangled Christmas lights have some magic built in, so that doesn't always happen. But if you have an old strand that you bought 30 years ago, this is exactly what happens. One bulb burns out, all the lamps go out. So there's only one path for the current to flow, and it goes through every single device in the series circuit. Now, a parallel circuit looks, what is going on here? Looks like this. And this is like the outlets in your house. You plug the toaster into one, you plug your TV in the other, you plug a floor lamp into the third. And if one of those burns out, the others still work because they're all connected in parallel. So a parallel circuit provides multiple paths for the current to flow. You see the difference between the two? Here we have one path, and here we have multiple paths, multiple parallel paths. And if we look at more complex circuits, they are all built out of series and parallel subcircuits. So when you zoom into a small piece, you'll see these things are in parallel and these things are in series. And then you zoom out and you just see a big mess of wires and lines and components drawn on the circuit diagram, and you have no idea what's going on. But once you zoom in and look at the individual component level, this is what you see. You see either a parallel or a series circuit. So now we have a few questions, and then we'll move on to Ohm's law. Electrical current is measured in which of the following units?
D.
Anybody? D, it's amperes, yes. We measure current in amps or amperes. And what is the name of the flow of electrons in an electrical circuit?
Voltage?
No, the voltage is the one that pushes the current through the wire. So the current is the actual flow of electrons. In the beginning, it's confusing. Which one is the voltage? Which one is the current? You'll get better at this. So voltage is the one that pushes, going back to this little drawing here.
Oh, yeah.
Voltage is the one that pushes, and amp, the current, is trying to flow through that wire. In this case, there's not much flow going on. This guy is stuck, but he would like to flow through the wire. And the resistance, ohm, is restricting this. So what's the name for the flow of electrons? That's the current. What is the electrical term for the force that causes electron flow?
Voltage.
That is the voltage, yes. So this is the guy who's pushing. Which of the following describes alternating current?
C. No. Alternating positive directions, yeah. Oh boy.
So was it going positive to zero, positive to zero? Was it going negative to zero, negative to zero? Or was it going positive and then through zero back to negative and up again to
Yeah,
positive?
through zero. It was going positive to negative, back to
Yes.
positive.
So that would be C, current that alternates between positive and negative directions.
Okay.
And because these are so different, D cannot be correct. So that eliminates one of them right away. Which instrument would you use to measure electrical potential?
D.
B.
D was a good guess, but it is actually B. So
Okay.
voltage, we also call electromotive force and electric potential. So there are three different terms that we can use to describe voltage. And of course, they're confusing you here and they're throwing electric potential at you. And you need to know, okay, this is voltage. So I use a voltmeter. So three names for voltage: actual voltage, electromotive force, and electric potential. So voltmeter. Which instrument is used to measure electric current?
E. Excuse me, D.
It's D. So electric current we measure in amperes or amps. So we use an ammeter to measure that. In which type of circuit is DC current the same through all components? Anything we can throw away right away.
Throw away branch and resonant.
Yes, because we haven't heard about them. So it has to be either a series or a parallel. So in which of these is the current the same through all components?
Would it be parallel?
So parallel is this one. We have multiple
Yes.
paths for the current. If this is a 100-watt bulb, this is a 50-watt bulb, and this is a nightlight, a 6-watt bulb, the current here would be relatively small. Here it would be like a medium amount, and we would have a lot of current here. So in a parallel circuit, the currents are not the same. What is the same is the voltage, because all of these are connected to, let's say, a 12-volt battery. When we measure from here to here, it's 12 volts. If we measure from here to here, it's 12 volts. And when we measure from here to here, it's also 12 volts, because they're all connected to the plus and minus pole of this battery. So here is our series circuit. In this case, what is it doing? My mouse is like really sensitive today. I connect all the bulbs together, and the current that flows through my first bulb is also flowing through my second bulb. 1 ampere, 1 ampere, 1 ampere. So the current is the same. The voltage that we have is different, because only the beginning of the first bulb and the end of the last bulb are connected to my battery. What's happening between these 2 points voltage-wise, I have no idea. But what I do know is that the current is the same. I'm pushing 1 amp in here, 1 amp is coming out here. 1 amp is going in here, 1 amp is going out here, and so on. And the same 1 amp gets provided by the battery. Does that make sense? So two different things that are constant based on what circuit we have. For the series circuit, the current is the same through all components. For the parallel circuit, the voltage across each component is the same.
So does that mean then if they were the same rated lamps in each R1, R2, and R3, that R3 would be more dim than 2 and dimmer than 1?
If they're all 100-watt bulbs, they would be exactly the same, assuming you buy them in one big box. They come off the manufacturing plant at the same time. They were all created very much alike. They would all be the same amount of brightness. But if you have, go ahead.
If they were getting different current, would that dim the lamps?
So the current that flows through a bulb in this case is determined by the wattage on that lamp. So a 100-watt bulb would draw more current than a 50-watt bulb. And a 50-watt bulb would draw more current than a 10-watt bulb.
Okay.
But if they're all 100 watts, they would all draw the same amount of power. Or the same amount of current, I should say. So if we don't know what labels are on these bulbs, the only thing we can say about this circuit is that the voltage across all the bulbs is the same. We don't know anything about the current. In order to determine what the current is, we would either have to measure or we would have to do some math. And more about that in a few minutes. So let's go back to in which type of circuit is DC current the same through all components? So now that we went back to those two different circuits, what do you think, in which one is the current the same?
A.
It's A, it's a series circuit, yes. And then, in which type of circuit is the voltage the same across all components? Again, we know it's not resonant, and it's not branch. So it's the parallel, it's the other one. So it's one of two. And current is the same for series. The voltage across the components is the same for parallel. How is a voltmeter connected to a component to measure applied voltage? So think of the two different types of circuits. If we want to make sure we are measuring the voltage that is supplied to a component, how do we connect our voltmeter? We're doing this in parallel because we know in a parallel circuit, the voltage across all components is the same, which also means the voltage across our voltage meter would be the same. If I want to know how much voltage goes to my toaster, I don't have to disconnect the toaster and put my probes into the outlet where the toaster is usually connected. I can go to the outlet that is 3 feet over because I know they're all connected in parallel and measure there. And I get exactly the same voltage that my toaster is getting. So we've done voltage and the parallel. Now we're looking at when configured to measure current, how is a multimeter connected to a component? So first thing is, what is a multimeter? You don't go to the store and buy a voltmeter or an ammeter or an ohm meter. You actually buy a thing that can measure all these things and a few other things in the same box, and we call it a multimeter. It has a big switch on the front, and you switch it from voltage to current to resistance to capacity to frequency potentially, and maybe a few more things. So that's what a multimeter is. So when we configure that to measure current, how do we connect it to a component?
I'm just going to say in series.
Yes, in series, because think of that strand of Christmas lights. If you want to measure how much current is flowing in there, you could cut that strand anywhere and put your ammeter in there. And then, of course, you have to bring out your electric tape and your soldering iron and fix it again. So we don't want to do that, but that's what we would do to actually measure the current in that series device. So current is the same regardless of where we are in a series circuit. Which of the following can damage a multimeter? So you should have seen this when you worked through the chapter. Does any of this ring a bell?
Having your multimeter set in the wrong setting. If you're measuring, if you want to measure for amperage, but you're on voltage or resistance, so you want to make sure that you're on the proper scale.
Right.
If you're measuring for 12 volts, you want to set low. If you're measuring for higher voltage, you want to set something that's going to measure 120
Okay.
or 240.
Yep. Okay. So that eliminates two of these options. B and D are not about wrong settings. So that leaves A and C. And which one do you think will damage the multimeter?
Having your meter set low and measuring high voltage.
But that's not one of the options here, unfortunately. So the option is either attempting to measure resistance using the voltage setting or attempting to measure voltage when using the resistance setting. So which of these two do you think will damage your meter?
Seems like A.
The right answer is actually C. So when you are in the resistance setting, what the multimeter does is it actually has a battery in it, and it pushes a small current through the probes. And then when you clip them on a resistor, there's a small current flowing through these probes and the device. When you have it in resistance setting and then you apply a large voltage, it will actually burn out that circuit that is trying to measure the resistance. So in this case, C is the right answer. There are other ways to damage your meter, Brad, but this one is asking for attempting to measure voltage when using the resistance setting. Robert?
You know, I kind of wanted to say C, and all I was thinking of was that picture with that rope around that constricting.
Yeah.
And that was making me think of measuring or the resistance would be the issue on damaging or the resistance is what would I guess like damage it.
Yep.
Is that all right if I remember that for a test?
Whatever you remember, whatever trick you can come up with, as long as you can pull out the right answer, that's all you need. But the real theory behind it is there's a battery in your meter, and it requires a small current to flow. And when you hook that up to 110 volts to your outlet, all of a sudden you will push a lot of current through that meter, and magic smoke will come out. And then you can try to push that smoke back into those components, but usually that doesn't work very well.
Yeah, no, it's not going to work. All right.
Which of the following measurements are made using a multimeter? So which ones of these look familiar?
Voltage and resistance.
Yes,
Are
that
familiar.
is the right answer. So this is what we would measure, among other things, with a multimeter. We would not measure signal strength or noise, and we would not measure impedance and reactance, whatever they are. So it's voltage and resistance. What reading indicates that an ohm meter is connected across a large discharged capacitor? So we haven't talked about capacitors yet, but capacitors are things that can store electrical energy. And when you apply a voltage to a capacitor, you are charging it up a little bit like a rechargeable battery. And I said, in our ohm meter is a battery, and we are pushing a small current through those test leads. So when you hook up your ohm meter to a discharged capacitor, there's a current flowing. And over time, that current will decrease. So it looks like, oops. It looks like the resistance that you're measuring is getting larger and larger over time because that current that flows gets smaller and smaller. So the right answer in this case is A, an increasing resistance with time. And unfortunately, some of these you just have to try to remember, because if you want to understand the theory behind it, we would have to dig a lot deeper than what we can do in here in this class. Which of the following precautions should be taken when measuring in-circuit resistance with an ohm meter? So a few questions back, what can damage an ohm meter?
Wasn't it voltage measuring resistance?
Yes.
Right? Something like that?
Yes. So if we measure voltage with an ohm meter or a multimeter in the resistance setting, we can damage that. So
yep.
Given that, which of the following precautions should be taken when measuring in-circuit resistance with an ohm meter? In-circuit means you took the lid off your radio and you want to measure in that radio, and you want to measure a resistor to figure out if that has the right resistance.
I guess A, ensuring that the applied voltages are correct.
Kind of, as long as the applied voltages are 0. So the right answer is actually B, ensure that the circuit is not powered. So we want to make sure that there's no voltage in this device. So it needs to be off.
Is that because the ohm meter is giving out?
Yes. So
its little power.
Yeah, we might damage our ohm meter or read wrong values if there is voltage in the system. So we want to make sure it's off.
Because if that battery wasn't in the multimeter, you'd have no guy pushing through to measure.
Yeah. And if you have another guy coming the other way and punching you in the face, would not be nice. So this is what would happen if you would have an external power applied to that.
Okay.
You had the other guy punching you in the face. So ensure that the circuit is not powered. Okay. Which of the following precautions should be taken when measuring high voltages with a voltmeter? So just from a common sense point of view, what do you think the right answer is?
I say B, right?
Yeah, high voltages are dangerous. And we want to make sure that our voltmeter and the test leads and everything we use are actually rated for use at that voltage that we want to measure. So if we know we are measuring 1,000 volts, you cannot use that cheap voltmeter that you got at Harbor Freight, because you might actually kill yourself in the process. So you want to use something that is actually rated for that voltage, so that you don't potentially touch live voltage, even though you weren't planning on, but your voltmeter is not up for the job. So B is the right answer. So this is actually a safety thing. And what is the unit of electrical resistance?
Ohms.
It's ohms, yes. So we have voltage for the electromotive force or the electric potential. We have amperes for current, and we have ohms for resistance.
Just a question with that one.
Mm-hmm.
In that last question, right? M. Haas, Columbus, whatever the hell that is, and Siemens.
Yes.
Is that how we would see it on the test? Almost like that ridiculous? Like I
You
see
would
that and I'm
see it.
thinking ohms just because that's what we've been talking about.
Yes.
You know?
So Coulomb, a French word here, that is a charge. If you take a rubber balloon and you rub it, you may know that it attracts things. Like when you put this
Yeah,
close
put it
to
on
your
your hair.
hair, it will actually pull the hair in its direction. That electric charge that you just created would be measured in Coulomb. Siemens is another real thing, and MHOS is also a real thing. What is my mouse doing today? It really does not want to cooperate. When you look at the characters here, it is actually OHMS. OHMS. So it has something to do with ohms, but we're not going into that in this class. So the only right one is ohms. And what you would see on the test are these four options in some random order. So ohms might be the first one, ohms might be the last one, ohms might be the second one or the third one. The only thing you need to do is say, oh, the others look ridiculous. Ohms, that is what it is.
Beautiful. I love it. Thank you. Thank you.
Why are metals generally good conductors of electricity? So what did we say about current? What's the flow of current? What's moving in a wire?
Electrons.
Electrons
are moving. So why do you think metals are generally good conductors of electricity? What do they have?
Free electrons?
They have a lot of free electrons, yes. So electrons are related to current. If you store this somewhere in the back of your mind, you should be able to figure out that metals are good because they have many free electrons. Electrons are good for conductivity. And which of the following is a good electrical insulator?
Glass.
Yes, so we have three metals here and one non-metal. The non-metal, the glass, is the good insulator. What type of current flow is opposed by resistance?
E.
It's D, it's all of them. So it doesn't matter what type of current you have. A resistor will oppose the flow of current, regardless of whether it's direct current, alternating current, RF current, or any other current that you can come up with. And this is the end of our first module. I know this was a lot, and there's actually quite a bit more to go. So there's a pretty good chance we won't have time to go over everything today. So, excuse me, you need to work on the questions that we won't get to on your own. Slideshow, play from start. Okay. So, Ohm's law, power, and we've already talked about the metric system last week. I took this out because otherwise it would have been even more stuff today. So here are our three guys again. Again, this is all you need to know about Ohm's law. Almost. So Ohm's law is the mathematical formula that tells you how voltage, current, and resistance are connected. And we said E represents the voltage, I represents the current, and R represents the resistance in our formulas. So the Ohm's law can show up in three different flavors. We can say resistance is voltage divided by current. So I measure 9 volts on a 9-volt battery. I know that there is a current of 1 amp flowing, and then I can calculate what the resistance is that is connected to that battery that makes 1 amp flow by dividing 9 divided by 1 amp. That gives me 9 ohms. Or I can say the current is the voltage divided by the resistance. So this time I go to the store and buy a 9 ohm resistor, and I put that across a 9-volt battery, and then I say, I don't want to cut into that circuit to measure the current. I can calculate that. And I can calculate that by taking my voltage, 9 volts, divided by my resistance, 9 ohms. 9 divided by 9 gives me 1 amp. Or I can say the voltage is the current times the resistance. So I don't have a voltmeter, but I have an ammeter, and I can measure the current that's flowing through my resistor, and it's 1 amp, and the resistor has 9 ohms printed on it. Then I can calculate the voltage that is applied to this resistor is current times resistance. 1 amp times 9 ohms gives me 9 volts. So it's 3 different ways to express this Ohm's law, but it always gives me the relationship between a current, a voltage, and a resistance. And the way you would figure out which formula to use is with this circle here. So when you get to the testing site and they give you your questions and your answer sheet, what you do is you turn the answer sheet around and you draw that circle on it. And you put the E in the top, you draw a line, and then you put I and R at the bottom. And then when you have a question, you say, what do I need to calculate? And that is the piece of information that you cover up. And if you then end up with I and R next to each other, you know you have to multiply I and R. So we are dealing with this form here. If you say I need to calculate I, you cover up the I, you have E over R, that means voltage divided by resistance. So this is the second form here. Or you cover up the R, and then you have E over I, voltage divided by current. So this would be the first variation of Ohm's law here. So by covering up the piece that you need to calculate, you can figure out what your formula will look like without having to remember all 3 versions. Does that make sense? So this was it about Ohm's law. Let's take a look at some of the questions. What formula is used to calculate current in a circuit? So we want to know the current. We go here, we cover up the current I. What do we have left? E over R. What does that mean? Voltage divided by resistance. So let's take a look at this here. Is there a voltage divided by resistance? Sure, B. B is our right answer. Does everybody agree on this? I hope nobody says C or D, because pluses and minuses we do not use in Ohm's law or the power law, which we'll talk about in a minute. So we can eliminate all the ones with pluses and minuses right away, because we only deal with multiplying and dividing. But in this case, it is the voltage divided by the resistance. What formula is used to calculate voltage in a circuit? So again, we cover up the voltage, E. We are left with I next to R. That means I times R. And we have that here in A. Again, get rid of the plus and minus right away. This is not Ohm's law. Does that make sense? So without having to remember every single variation of that formula, if you just have that diagram, that circle, then you can figure out which one you need to use, and again, what the right formula is in that case. And then, of course, there's one more left. What formula is used to calculate resistance in a circuit? And if you do that, you will find out it is voltage divided by current. And now we're doing this with actual values. And I don't want to go over every single one of these questions because they're all very similar. So I want to just do a couple so that you get the gist of it and you can do the rest on your own. What is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? So which one is the one that we need to know, that we need to calculate? What's the question asking for?
R.
It's the resistance, yes. So we go back here, we cover up R. What is left? It's voltage divided by current. So we go here, voltage, 90 volts divided by current, 3 amps. 90 divided by 3 gives us 30. Right answer is B, 30 ohms. And here is the right answer. So all these questions follow the same pattern. It asks you to calculate one thing. And as long as you can figure out what that one thing is, and you have your little diagram, you can figure out what the correct answer is. What is the resistance? We cover up resistance. We are left with voltage divided by current. Voltage is 12 volts. Current is 1.5 amps. I need to pull out my calculator. So that gives me 8 ohms. 8 ohms is the right answer. And by the way, you can bring a simple calculator to the test. As long as it's not programmable, you can bring that calculator. So I'll just skip over these now. Here we have a different flavor. What is the current through a 100 ohm resistor connected to across 200 volts? We want to know the current. We cover up the current. We are left with E over R, voltage divided by resistance. So voltage is 200 divided by 100 ohms gives us 2 amps. Right answer, C, 2 amps. And there are a lot more of these. So good news is you will only see at the maximum one of these questions in your test. And as long as you have that little diagram, you should be able to figure out how to calculate that thing that the question is asking for. Any questions about Ohm's law? Okay. So here is the second formula that we need to deal with today. It's about power. When we run current through a wire, through a resistor, it gets hot. That is the electrons actually doing some work by expending energy, or they're making light in a light bulb. Anytime energy is expended, power is consumed. Electrons moving resistance expend electrical energy and consume power. Power is the rate at which energy is consumed, and we measure power in units of watts, and we use a capital W for that. So you buy a 100-watt light bulb. That means that light bulb consumes 100 watts and converts that to light and heat. Portion of it gets converted to heat. Hopefully a big portion gets converted to light. There's a formula involved, and it has three components. We deal with power, voltage, and current. And again, we can put this formula into three different variations. We can say power is voltage times the current. We can say voltage is my power divided by current, or we can say the current is power divided by the voltage. And this time we are creating a pie chart, PIE. So again, we draw a circle, we put P in the top portion, draw a line, and then I and E in the bottom portion. And we do exactly the same thing. We cover up the one thing that we need to calculate. And the arrangement of the other two letters will tell us what the formula looks like. E divided by power divided by current, power divided by voltage, or voltage times current, or in this case, actually current times voltage. So just like what we did with Ohm's law, we now apply this to our current, our power equation, I should say, our power equation. Does that make sense that we can use the same process that we used for Ohm's law here? Because again, we have three different things that are either given or we need to calculate. Here are the questions for the power chapter. Electrical power is measured in which of the following units?
Watts.
Watts. Any idea who this unit is named after? There was a guy named James Watt, and he invented a steam engine. And steam engine, of course, creates power, and they named this unit after him. Which term describes the rate at which electrical energy is used?
Power.
It's the power. We measure the power in watts, and we call the rate at which energy is used the power. And here are our formulas. What is the formula used to calculate electrical power in a DC circuit? So let's go back to this one. How do we calculate power? if you want to calculate power, we're covering up the P. And then we are left with I and E next to each other. That means we take current times voltage. So do we find that anyway in here? It's A, yeah. So, and just like with Ohm's law, we can say C and D is not correct because we are not doing minuses or pluses. It's either multiplication or division. So C and D is definitely wrong, and it needs to be one of the first two. And it is power is our voltage times our current. So if I have a radio that I want to put in my car, I know it consumes 12 volts, and I put my amp meter into the power line and I key up and it measures 10 amps. And then I know 12 volts times 10 amps, that's 120 watts. So my battery needs to be able to provide 120 watts. And then you can go and buy the battery. So this actually has practical implications for what we want to do with our radios. And here we have exactly this example. How much power is delivered by a voltage of 13.8 volts DC in a current of 10 amps? Does anybody want to guess?
138 watts.
Yes, so it's 13.8 times 10 is 138. And there are a few other variations of this, so I'll just skip over them. We've seen this before. We've now added ohm, watt, volt, and ampere. So there are a couple more to go. And this is the end of our second module for today. And again, I know this is a lot of new information for you, stuff that you have not dealt with before if you don't have a background in electricity. So any questions about Ohm's law and the power law? Okay, the next one, this is about electrical components. And unfortunately, it's again a lot, and we will not be able to get through every single question. So please do this on your own time. And if you have any problems, send me an email and we can talk about this next week. So we've learned about the basics of electricity: voltage, resistance, current, power. Now we learn about components that allow us to modify some of these aspects that we've heard of so far. Here's a whole pile of components. And when you open up your radios, there's a pretty good chance you'll find stuff like that in there. Now, we don't need to know about what every single one of them does in great detail, but we need to remember a few things. So it's all about controlling the flow of current. If we want to have music or sound come out of a loudspeaker that's connected to our radio, we are modifying, controlling the flow of current. When it gets loud, there's a lot of current flowing into that speaker, If it gets quiet, there's only a little bit of current flowing in that speaker, and it's going back and forth because it's AC. So we need a way to control that flow of current, and there are a number of different electronic components that allow us to do that. When we talk about electronics in general, in order to know what I'm talking about, I use a schematic diagram that shows how components are connected to each other. Now, if I would be better at drawing, I could do elaborate drawings of what the components look like on a circuit board, but that would not really help us much. First of all, I'm not good at drawing, so you wouldn't even know what I was trying to tell you, but also it just takes too long. So we use these simplified schematics to communicate how components need to be connected. On a schematic diagram, we use symbols for the different components, and each component has a very specific symbol, and we need to be able to recognize some of them. So this is a schematic diagram. The lines and the dots on the schematic represent electrical connections between the components. So I have a transistor here. What that is, not important right now. We know it has 3 wires coming out of it, and I'm connecting things to these 3 wires. So everywhere we have a line, that is an electrical connection. It's not necessarily showing me how, as far as the arrangements of the components goes, how it's connected. I just know there is somehow a connection, electrical connection between those 2 points. Wherever I see a dot, there is an electrical connection. So this resistor here is electrically connected to this wire up here. So the wires and the dots represent these electrical connections and not the physical arrangements of these components. The first component that we want to talk about is the resistor. And the resistor is, the function of the resistor is to restrict the flow of current. We already know about that because that's a fundamental concept of Ohm's law. Now we learn about the schematic symbol. So that is that squiggle here. And a resistor can come in a variable form, and that is when we have an arrow that points to that resistor. And that indicates that we can change the value of this resistor. And this is, for example, used in the volume control of a radio. So oftentimes there's a variable resistor in there. This is what a resistor might look like, and it has colored bands. And if you know what the different colors mean, you can actually determine what the value of this resistor is. Orange, for example, is 3. Purple is 7. So you can then figure out what the value of this resistor is. The next one that we want to talk about is the capacitor. The function of a capacitor is to store electrical energy. It's important that it's not just energy, it is electrical energy. And we call this function capacitance. This is what a capacitor might look like. This is what the schematic symbol looks like. And you see there are 2 plates here, conducting plates with nothing in between them. And this is actually what a capacitor looks like. It stores energy in an electric field created by voltage between the electrodes, these 2 plates, with insulating dielectric material between them, plastic, in other words. Used to be paper. Nowadays, it's some form of plastic. It acts a little bit like a battery because it can store electric energy. And it also comes in a variable flavor. Again, we have that arrow that is going through that capacitor. And that would be used, for example, as a tuning mechanism in an old radio. And when you look at a capacitor, a tuning capacitor in an old radio, you actually see those plates with air in between. So they're not connected, but because of that, you can actually store electrical energy when you apply a voltage to the capacitor. So a lot of the information that I have here very condensed on these slides actually show up as answers to questions. An inductor stores magnetic energy. Capacitor stores electric energy. Inductor stores magnetic energy. And we call that function inductance. A coil of wire around either a core of air. A core of air means something like we have down here, just a coil of wire, or around a magnetic material like iron or ferrite, which we see here, creates an inductor. So just a few windings of wire in air will be an inductor. And it can store energy in a magnetic field created by the current in the wire. So when we run current through that wire, we are creating a magnetic field. And the schematic symbol is this here, and it kind of looks like as if we would have cut through that coil. And again, it comes in a variable way, in a variable form that we can again use to tune a radio. So when you look at this symbol here, and then look at the symbol of a transformer, it looks like there are two inductors in there. And this is exactly what a transformer is. There are two or more separate, not connected windings around a metal core in a transformer. And you see the metal core illustrated by these two lines here. So a transformer is a pair of inductors sharing a common core. And because of that, they share their magnetic field. And we use that to transfer energy from one coil to the other coil without a direct connection. And usually the number of windings on these two inductors are not the same. And because of that, we can actually change the ratio of voltage and current. So we could have 110 volts go in here, and then 12 volts come out here. So by changing that ratio of how many windings we have on the first winding versus the second winding, how many turns we have there, we can control what the output voltage will be like. And we can either bring it down or we can bring it up. I could also go in here with 120 volts and come out with 1000 volts here. So in that case, I would have a different ratio of turns. So we use that to change the ratio of voltage and current. We already know that resistors are measured in ohms, capacitors are measured in farads, capital F, inductors are measured in Henry, capital H. When we go back to our schematic here, we see we have three different resistors in there. We now know that these are resistors. This one is called R1, R2, R3. So we actually give them numbers in our schematic so that I can call you up and say, hey, take a look at this schematic of this radio and look at R27. I think that needs to be a different value. So by saying this thing is called R for resistor, and then it has a number 27, we can exactly identify which of the many, many resistors in that schematic we are talking about. So we call them component designators. So every schematic symbol has a designator to denote which component it refers to. For example, the 10th resistor is R10. We use R10, C7, L15, and other letters for other types of components. So the first few components that we looked at, resistor, capacitor, inductor, transformer, they play certain roles in a schematic. In addition to that, we have something that potentially is used to communicate with us, and we call them indicators and displays. So an indicator communicates some status. It's on, off. The red LED is on when the power switch is on. It's off when the power switch is off. So that tells me right away whether the device is on or off. In our car, we have the blinkers, and if I put the turn signal on, we get some indication that the blinkers are going. So these are indicators. They could be LEDs, light bulbs, could also be a symbol on a more complex display, like for example on our phones, we usually have some indication about how strong the Wi-Fi signal is. Could be audio tones. Our smoke detectors are beeping at us and indicating that something is wrong. Displays are more complex. They communicate values or text. Could be numeric values, you're going 55 miles an hour. Could be a warning, you're not wearing your seatbelt. Or could be a message, tire pressure is low. We are measuring whatever the number is. They come in digital and analog form. So we either have needles on them, this would be the analog meter, or numbers, 55 miles, you're going 55 miles an hour, just 2 digits. And we usually use LCD screens or OLED screens or something like that. Next one that we want to talk about gets a little bit obscure. So we said capacitors and inductors can store energy. One of them electrical energy, the capacitor. The other one magnetic energy, as the inductor. So they're not dissipating energy like a resistor. They're actually storing energy. They are taking energy out of the system for a certain amount of time and then putting it back in. The storage of energy creates an effect that we call reactance. And we use the capital X as a symbol for that. And it kind of acts like resistance, but only in it opposing the flow of AC current. It doesn't do anything for DC current. Resistors affect DC current and AC current in the same way. These components, capacitors and inductors, only affect the flow of AC current. A capacitor has capacitive reactance, XC. Inductors create inductive reactance, XL. And the effects of each are actually complementary, and they can cancel each other out. Interestingly enough, Oh, it's not on this slide yet, but let me just take this. We are measuring reactance in ohms as well. So we're measuring resistance in ohms, but we are also measuring reactance in ohms, but only when it comes to AC current. Now, in real life circuits, usually there's a combination of resistance and reactance. So if you use any real inductor, it's not just a pure reactance. There's also the piece of wire that has a certain resistance. So it's a combination of a resistor and an inductor. And we call that combination the impedance. And we use the capital Z for that. So impedance now represents the circuit's opposition to both AC and DC currents. So a part of it is for DC and a different part is for the AC current. And what makes things even more complicated is that the component's reactance actually depends on the frequency. And this is stuff that you just need to learn because in order to understand why that is, we would have to spend a lot more hours on this. The inductive reactance XL increases with frequency, whereas the capacitive reactance XC decreases with frequency. And you can kind of see that when you look at an inductor. So we say this one, the reactance increases with frequency. If we have DC current, we have 0 hertz frequency. And then this is really just a piece of wire. It doesn't do much besides just being a piece of wire. Whereas when we crank up the frequency, it loses it's just a piece of wire characteristic and it becomes this inductor. And then that reactance increases as frequency goes up. And the opposite is happening with the capacitive reactance. Now there's an interesting point where when you have one inductor and one capacitor, and you look at the frequency for which the reactance components of these two elements are the same. And then they cancel each other out. And we call that the circuit's resonant frequency. At this point where they cancel each other out, this resonant circuit only has resistance. So the reactance of it is 0. And that means it affects AC and DC current equally. And here we have one of these circuits. So we have an inductor and a capacitor. And there is a resonance frequency that we can calculate, which we are not doing in this class. We also call this a tuned circuit. And this is important because this is actually what we use in our radios to tune it to one specific frequency, the resonance frequency of this circuit. So if we make this capacitor adjustable, we can actually tune that radio to 1280 AM or whatever the frequency is that you want to listen to. So what we've looked at so far, we call passive components. They don't do much besides basically trying to oppose the flow of current in some way. What we are looking at now, semiconductor components, we call active components, and they can actually do some magic. So when we look at silicon, it is an okay conductor, but nowhere near as good as metals. It's better than glass, but a piece of metal, even the worst piece of metal, is still much better than a piece of silicon when it comes to how well they conduct. But we can play some tricks with them, and we can add impurities to these semiconductors and create pieces of material that have more electrons than usual, which we know when it comes to metals, this means a good conductor, or fewer electrons than usual. And we call one the N-type of a semiconductor, which is the one that has more electrons, and the other one is a P-type with fewer electrons than usual. And when we now bring these P and N materials together in certain physical arrangements, we can actually control the current flow through such a semiconductor. And the most simplistic semiconductor that we can build is the diode. And the trick that the diode has up its sleeve is that current is only allowed to flow in one direction. A diode has two electrodes, anode and cathode. And if we add a more positive voltage to the anode, we have current that flows through the diode. If we put more voltage on the cathode side, it blocks and there's no current flowing back. So current will only flow in one direction. It cannot flow the other way. And with that, we can actually use this diode to rectify AC current and make DC current out of it. Diodes that are used to change AC power to DC power are called rectifiers. And this is the answer to one of the questions on the test. So when you see rectifier as one of the answers, that is the right answer. The schematic symbol is down here. They come in different flavors. LEDs, light emitting diodes, are one flavor of diodes. So in addition to only letting current flow one way, they also start to emit light glow when that current is flowing. And we designate them in a schematic with a D or sometimes with a CR. So here we have two pieces of semiconductor material. One N, one piece, we bring them together and they create a diode. When we add another one, PNP or NPN, we can create something that's called a transistor. And the function of a transistor is to control large signals with a small one. So it's like an electronically controlled current valve or an electrically controlled amplifier. So with a small signal, we can make a big signal, and that means we are amplifying this small signal. And we use a different word for that, and we call that gain, which also is the answer to one of the questions. We can also use transistors as switches, as electronic switches, and turn current on and off, a large current on and off with a small current. They come in different flavors. We have bipolar junction transistors or BJTs, and we have field effect transistors or FETs. What both of them have in common is this connection here is is controlling what's flowing down here, from here out here, or from here out here. So transistors are used to control large signals with a small one. When we amplify, we have something called gain, but they can also be used as electronic switches. So this is a bipolar junction transistor. It has 3 layers of N and P material, and we either call them NPN or PNP transistors. They have a slightly different schematic symbol. One of them has the arrow pointing out, the other one has the arrow pointing in. Not important for this class. This is a field effect transistor. It has a conducting path or channel of N and P material connected to the drain and source electrodes, and then we have this gate, and we apply a small voltage to the gate, and we can control a large current between drain and source. Now, if we take a whole bunch of these and put them on a bigger chip, we end up with something that's called an integrated circuit. An integrated circuit, or IC, is a collection of components contained in one device that accomplishes one specific task. And this could be a little amplifier, for example, which we have down here, that little triangle, that's a symbol for an amplifier. Or it could be some logic device. We have that up here. So there's no one schematic symbol that we use for ICs. These are all specific to whatever function that IC provides. For the test, what we have here, the integrated circuit is a collection of components, blah, 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 is what you need to remember. We have protective components, fuses, and circuit breakers. They're really important because they help us to avoid things blowing up, things busting into flames, and potentially causing major damage. A fuse blows, it's a one-time thing. Once it blows, it's done. You throw it out, you buy another one with hopefully the exact same rating as the one that you are replacing. A circuit breaker is like a reusable fuse. It trips and you can reset and reuse it. So same applies to circuit breakers. Always use the proper rating when you replace one. Replace it with one that is exactly the same value. There are different schematic symbols that we use for fuses and circuit breakers. I don't think you need to recognize them for the schematics that we're dealing with in this class. Switches are used to interrupt or allow the flow of current, and they come in different flavors. And there are 2 things that we need to be aware of. One is called the pole, and the other one is called the throw. So we count the number of circuits that are controlled by a switch, and we call that the pole. So here we have a single pole. We only have one circuit that gets controlled by the switch. This is still a single pole because we are now switching back and forth. We have one input and we have potentially 2 outputs, but it's still just one circuit. Down here, we have what we had up here duplicated and connected. So now we are actually controlling 2 different independent circuits, and we call that now a double pole. The other one is the throw, and that counts how many positions this switch has. If it's just an on-off, it's a single throw. If we can switch between 2 different poles, it's a double throw. If this would be 3 different things, I go one way to the middle and then the other way, and I can control, I can run my output, my input to 3 different potential outputs, we would call that a triple throw. And we combine these designators. So we have a single pole, single throw, single pole, double throw, double pole, double throw. And I think we need to at least recognize 2 different ones of these. Down here is a push button that does not stay down. It comes back up when you push it and release it. The switches, actually, you flip that switch and it stays in that position. Relays are just like switches, but now they are activated by a current in a coil, so by an electromagnet, which means we can actually control a switch electrically. They use the same names as far as poles and throws go as switches. When you cut open a relay, the moving switch is called the armature, not on the test. The contacts are named by when they are connected or how they are connected. So we have the common, we have the normally closed, NC, normally closed, and we have the NO, the normally open. So if we don't apply a voltage to the coil, the NC, the normally closed, is connected to the common. Once we apply a voltage, then that switch flips the other way, and the normally open is then connected to the common. And here are a whole bunch of other circuit symbols. The ones that we need to know are resistors, transistors, lamp, battery, capacitor, light emitting diode, variable resistor, transformer, variable inductor, antenna, single throw, single pole switch. We need to be able to identify them on schematic diagrams. So the next part of this will be questions. Any questions that you have about what I just went through, probably a little bit too fast, but unfortunately we don't have much time today. I'm not hearing anything. So this is just a quick summary that shows you the type of thing, the property, what we call it, the unit symbol, and what we use in a formula. So whenever you have any questions about that, this is all on one slide. So we have a whole bunch of questions, and again, we won't get through all of them. I want to pick out a few that are very representative of other questions. What describes the ability to store energy in an electric field? It's important that this is an electric field.
D.
It's the capacitance, yes. Capacitors store electric energy, inductors store magnetic energy. And this might just be, oh no, it's not the next question. What is the unit of capacitance?
A.
It's a farad, yes. And what stores energy in a magnetic field?
D.
It's the inductance. And what's the unit of inductance? It's the Henry. So we have ohm for resistance, farad for capacitance, Henry for inductance. What electrical component opposes the flow of current in a DC circuit? DC is important here. It is the resistor. The resistor does oppose the flow of current in a DC and AC circuit, but for AC, we also have the inductor and the capacitor. So because this is specifically for a DC circuit, the only right answer is the resistor. What type of component is often used as an adjustable volume control? So it's C, the potentiometer. The variable resistor is also called a potentiometer. Different word for a variable resistor. This goes the same way. What electrical component stores energy in an electric field? Oh, we just had that. What type of electrical component consists of conductive surfaces separated by an insulator? Which is also indicated by its schematic symbol.
Capacitor with the two lines?
Yes, it's a capacitor. What component changes 120 volts AC power to a lower AC voltage for other uses?
Transformer.
It's a transformer, yes. What is the unit of impedance? So this is a little bit confusing because we know ohms we use for resistance, but we also use ohms for reactance. And because impedance is the combination of reactance and resistance, we also use ohms for impedance. So it is ohms. What is impedance?
B?
It's the opposition to AC current flow. So I said resistance opposes AC current and DC current in the same way. Capacitors and inductors with their reactance and therefore impedance oppose AC current flow. So by figuring out the frequency that we have and how much we want to oppose that current, we can then determine what the component value needs to be. Too much for this class. We're not going into that level of detail. So impedance is the opposition to AC current flow. Which of the following is combined with an inductor to make a tuned circuit? We also call a tuned circuit a resonance circuit. And we use a capacitor and an inductor, either in series or parallel, doesn't matter for this class, to make one of these. So which of the following is combined with an inductor? It's a capacitor. Which of the following is a resonant or tuned circuit? So again, the answer here is an inductor and a capacitor in series or parallel. let me jump ahead a little bit. So there are 3 schematic diagrams that you might encounter. And they're all on one page. So you will actually get a couple of pages with questions, and one of the pages will have 3 schematic diagrams on them. You will only see questions, and very likely only one question about one of these diagrams. So when you look at these questions, make sure you know which figure it is referring to. So T1, T2, T3, T for technician, you will have all 3 of them, but you will only see one question at the maximum referring to either T1, T2, T3. Make sure you pick the right schematic. Otherwise, you will not get this question right. So there are a whole bunch of questions now that ask you to identify a component or give some information about a component. What is the function of component 2 in figure T1? So first we need to figure out what is component 2. And they're all numbered, so component 2 is this one. Any idea what this is? Is a transistor. And what does a transistor do? On a very basic level,
Which?
it controls the flow of current. So even without knowing exactly what it does in this circuit, we know it's a transistor. And what the transistor does, regardless of whether you use it in an amplifier or as an electronic switch, it controls the flow of current at a very basic level. And that's all they're asking for here. They are not asking you, what exactly is it doing here? And it's actually working as a switch, but not important. What it is doing is controlling the flow of current. So C is the right answer. And then we have questions of this type. What type of switch is represented by component 3 in figure T2? So we look for T2. Here it's easy because it's right there, but in the test, you actually have this on a separate page. You find T2, then you look for component number 3. Here's the switch. So what type of switch is that? Oops. So we have single pole, single throw, single pole, double throw, double pole, single throw, double pole, double throw. We count, it's a single pole, single throw. So we count how many circuits are involved here. 1. How many positions does the switch have? 1. So it's a single pole, single throw. And I think this is the only one that you need to actually be able to identify, but I could be wrong. What's a relay? It's an electrically controlled switch. These are now the diagrams where we need to identify components. What is component 1 in figure T1? Oops. So here is our component 1. What is this?
It's a resistor.
It is a resistor. You look at the different options that we have here, it is a resistor. And then they go through all the components. Number 2, number 3, and number 4. Number 4 is a little bit different because it's actually not a component, it's a ground symbol. And all the grounds are actually connected to each other with an invisible wire. Oh no, figure 4, component 4 is actually the battery. Never mind, it's the battery. Sorry about that. Get carried away. And then this is figure T2, same thing. It's asking component 6. We look at 6. What do you think this is? There are only 4 different options. It's a capacitor. Yeah. And then component 8, which is an LED. 9 up here, a variable resistor or potentiometer, but they call it a variable resistor in this instance, and so on. And then we move on to the third one, T3. What is component 3? We look at it. The options given here, it's a variable inductor. So again, you will see at most one of these questions on the test. And this is the end of module 3C, and we have a few more things to look at. Just a second. Hopefully this will be quick. So we have a few radio related things that they want us to go over. Any questions about the components? So again, we don't have the time to go over every single question, but please do that on your own time. Go over them again and again until you get a good feeling for what the right answer is. And if you have any problems, please send me an email and say, hey, this is not working for me. And I will try to go over that again next week. So here we have types of radio circuits. So we've already talked about the basic transceiver. A transceiver is a combination of transmitter and receiver, and with an antenna switch between the two, so that the antenna is either connected to the transmitter or to the receiver. And then to make the whole thing work, we also need a power supply. We need to somehow provide power to our radio. The transmit receive switch allows the antenna to be connected to either the transmitter or the receiver. In the olden days, that was actually a mechanical switch outside of your two boxes. One was a transmitter, the other one was a receiver. So you had to flip a switch. With our modern radios, this is done automatically. We talked about a repeater, radio on the top of a mountain, tall antenna mast that can receive signals from a low power station, your handheld radio, for example, and then at the same time as it receives your signal, retransmits that signal with a much more powerful radio on a different frequency, but on the same band usually. Here we don't have a transmit receive switch. We have something called a duplexer that actually is able to split out certain frequencies and let them go through the same cable in two different directions at the same time. Not something that we need to understand, just a little bit of background that there is something a lot more complicated involved. What happens during radio communication when we transmit a signal? We take some sort of information and we add that to a radio wave, and we call that modulation. And then we take that radio wave and we extract that piece of information, and we call that demodulation. There are different levels of complexity. Morse code is really simple to both generate and decode, as long as you have a brain doing that. When you want to do it with a computer, it gets a lot more complicated. But then we have other modes that actually require a computer because we can no longer do this on our own. Here are a few things that you will find in a radio. One is an oscillator, which is a circuit that creates a signal of a specific frequency. And it's a little bit like an amplifier that amplifies its own output signal. And if you know what happens when you take a microphone that's connected to a PA system and you hold it in front of the loudspeaker, it starts to squeal really loud. You know how an oscillator works, because we're doing exactly the same thing, just without a microphone and a speaker involved, and we make this connection electronically. And this is how we can create signals. Filters are circuits that act on signals differently based on the frequency of these signals. A filter can reject, enhance, or modify signals. We'll go into more details later. Actually, we go into more details right now. So here are different types of filters. For a filter, we can create a high-pass filter that allows higher frequency than that cutoff frequency to pass through. Frequencies lower than our cutoff frequency will be attenuated. We have the opposite here, which is a low-pass filter. Frequencies lower than the cutoff frequency will go through, mostly unchanged, and higher frequencies will get attenuated. We can combine these two and create a band pass filter that only lets through frequencies from one frequency to another frequency. And anything below that gets thrown out, and frequencies higher than that get thrown out. Now, when I say throw out, you see they don't go down to zero right away. They gradually approach zero. So the closer your frequency is to that cutoff frequency, the stronger it will be. The further you get away from it, the weaker it will be. And then we create the opposite of a band pass filter, which is a notch filter that filters out one specific frequency or a small range of frequencies. I live about 2 miles from WHAM, the AM broadcast station, which usually transmits 50 kilowatts, which is a lot of power. And I have radio signals coming out of anything that has a wire attached to it. So in order to actually use my radio, I need a notch filter that is tuned for the frequency of that big transmitter in my backyard, so that I can get rid of these frequencies so that they don't overload my radio. Adding information modulation, we can modify different things. We can modulate the amplitude, we can modulate the frequency or the phase of our radio wave in order to put some information on top of that radio wave. And here is a little graphic that demonstrates that. So we have our audio signal here, which we call the modulator. Then we have our radio wave, we call the carrier. And then an amplitude modulation looks like this. So you see those mountains and valleys, that are represented in our audio frequency in our AM modulated signal as the envelope. And if we modify the frequency, you get to see how these squiggles get pushed closer together or stretched apart. So the frequency actually changes, whereas the frequency here does not change, just the envelope, the amplitude of our signal changes. And we do that with something that's called a mixer. So we can combine different frequencies with a mixer, and it creates a number of different output signals. Usually we want 2 of them. but we get others that we need to filter out. We get the sum and the differences of the input signals. So with that, we can do some math and figure out what the output frequencies will be. Here are two important terms. You will find them on the test. When we look at what a receiver needs to do, there are two tasks that are essential. One is to hear a signal, pull that out from the noise if it's really weak, and then hear only one signal and push all the others that might be in the vicinity away so that we can concentrate just on this one signal that we're interested in. Selectivity is a measure of how well a receiver can detect weak signals. So high sensitivity means I'm able to listen to the weakest of signals. A bad sensitivity is your signal needs to be really loud in order to actually make it through my receiver. And then we have selectivity, which is a measure of the receiver's ability to discriminate between signals that are close by. So sensitivity and selectivity. A preamplifier makes a receiver more sensitive. And a preamplifier is added between the antenna and the receiver. This is the answer to one of the questions. One more term, a transverter is a box or a gadget that converts a transceiver to operate on a different band, usually on a higher band. So for example, you have an HF transceiver, and with a transceiver, you can then transmit and receive on the 222 megahertz band. Or you have 144 megahertz radio, and with a transverter, you can then transmit and receive on the 10 gigahertz band. And then we have the questions associated with this chapter, but they are fairly straightforward, and you should be able to work through them on your own. I know we are 8 minutes late, so I don't want to keep you for much longer. I think you can do this on your own. And again, if you run into any questions, please let me know, and I will try to explain why something is the correct answer for a specific question. Any questions from you before I let you go?
Appreciate the review.
I know you're all exhausted after this whirlwind 2 hours. I know this is a lot of material. This is the most complicated chapter in the book. And when you study, please keep in mind, you can get 9 questions wrong. So don't drive yourself crazy and say, I need to get this. I need to get every single question. I need to remember every correct answer. There is some wiggle room. And if after a few more weeks you say this electricity is just not for me, try to get as many questions as possible and just ignore the others. And if all the other stuff you're solid on, then you should not have a problem passing the test. But don't give up too early. A lot of people eventually come around and say, yeah, I really don't understand why this is the right answer, but at least I know it's 138 watts. I've seen this question so many times. I don't know how to get to this number, but the right answer is 138 watts. And we saw that question earlier today. So again, don't give up. Don't get discouraged. it will get easier from now on. We will still have quite a complex task next week, but I think it's a little bit easier to understand than what we did today. And then after that, common sense will become a lot more important than when we talk about electricity. And if you don't have any questions for me, I hope that I will see you again next week. And please work through chapter 4 as much as you can while still reviewing chapter 3. And I hope you have a great week.
Thank you.
Have a good night.
Thanks.
Bye.
Thank you, Carl. Thank you very much.
You're welcome.